Good morning and welcome back to the course. So now what I'm going to do is I'm going to give a bit of a digression. My digression is in part inspired by the fact that we're getting ready to do something about viruses. We're living in a worldwide pandemic right now. There's a virus named SARS-CoV-2, which is propagating amongst the human population. And there's still much that we don't know, but there are things we definitely do know. And I wanted to comment on science as a way of knowing, as a style of trying to learn things, where there's a methodology that's set up to try to convince ourselves that we're not fooling ourselves. So the title of the vignette is Science is Not a Smorgasbord. And hopefully as I go along, it will become clear what I mean by that. The essence of it is this, that over the last thousands of years, the various edifices of mathematics and physics and chemistry and geology and biology and so on have assembled bankable, actionable, predictive knowledge about the world around us. I've already used this example many times, but I'm going to use it again. I can look up in a tide book what the tide will be at Ocean Beach in San Francisco on any given date in the years to come, and I can, aside from if something happens with sea level on those time scales, I can bank on it. It has to do with our deep understanding of the gravitational relationship between the moon and the earth and the sun and so on. So we don't get to pick and choose, and I'll say what I mean by that. So this is a fun, kind of weird, interesting map, I think from the late 1930s, called the Map of Physics. And I like it just because I think that it gives a sense of the fact that science is this giant continent where everything is connected, and there are interesting tributaries in the various rivers, and some of them go off to one place and others go to some other place. And the map of physics could be enlarged now to think about the continent of science. And the continent of science has one of its objectives is to, as I said a moment ago, to generate bankable knowledge that we can agree on. And I'm not talking about at the level of social discourse. I'm not talking about that at all. I'm talking about for practitioners that are interested in doing things like building bridges or building airplane wings or in building antennas or phones or figuring out how much heat they need to conduct away from a device, or even some new medicine or an X-ray technology or the ultrasound that was used, a portable ultrasound that was used to measure the position of my dad's heart after he had a lung removed. All those are based upon knowledge. There's no amount of just walking up to a guy and putting your hand on his chest and, kind of attempting to make a measurement like that ultrasound did. And so there's this giant connected continent of knowledge and approaches, and that is the continent of science. So what I really find amazing about this, and I've commented it on in the course, I'm a big fan of indirect knowledge. I think that a lot of the predecessors of things that we now see, directly in the modern day and age were originally seen indirectly. And I can think of no better example. This was certainly the example that got me interested in science, I have to say, than Eratosthenes and the measurement of the radius of the Earth. So the radius of the Earth is something that's been measured over and over and over and over again, tons and tons and tons of times. And, we can talk about the error bars. We can talk about how tightly we can bound that idea of the radius of the Earth. But nothing essentially has changed. I mean, the 19th century saw a very interesting debate about the oblateness of the sphere, whether it was a larger radius at the poles or at the equator, and that was a debate that had to do with the rotating Earth and so on. And that's super fun and interesting in its own right. But this very old school thing was the idea that by using a little trigonometry and measuring the shadow cast by the noonday sun on summer solstice in two different places would suffice to determine the radius of the Earth. And what I want to say is Eratosthenes' measurement of the radius of the Earth has stood the test of time. Sure, again, it's, as I said before, we can talk about how accurate the number is, but it's pretty accurate. And what I would say is that we send rockets into space, people go to the moon, they take cameras, they take pictures. There's a self-consistency of that knowledge, and there's an independence of perspective. The answer to the question of the radius of the Earth does not depend on what era you lived in. It does not depend on what country you come from. It does not depend on your age, any of that. It just is a thing that we can, if we all undertake a careful measurement and we're not in some weird agenda type of mode, we will find the same result within some error. I had a really wonderful experience a few weeks back at Caltech. We're in the middle of doing interviews to try and decide who's going to be accepted for grad school. And I spoke to a young woman who was a physics major and who's fundamentally interested in biology. And she really blew me away, I have to say, because she explained to me the moment that she knew that physics was for her. And let me tell it to you. So she said that in her class, they did this was high school, I think. They did a very careful job of reasoning out the question of, if I release a ball from an inclined plane, where should I put a bucket on the ground so that the ball will land in the bucket? And they didn't do the experiment, and they didn't do any sort of phenomenology ahead of time. In other words, they worked out the laws of projectile motion by knowing, forget about air resistance, by knowing that the x velocity is constant, and therefore that the distance traveled in the x direction is v times t, where t is the elapsed time. The y direction, that one we know is 1/2 gt squared, and you can put those two things together and work out a parabola. And so what she told me was that how blown away she had been by this idea that by pure thought, by doing a calculation, and this is a feeling I have shared with her so many times, and I'm going to come back to it at the end, having to do with the age of the Earth. It's kind of incredible to sit down with a piece of paper, with your iPad, and to do a calculation, and to feel like the calculation is one that you could call any other person and say, here's the concept, here's the assumptions, here's the setup. Can you please calculate for me the distance that this thing will travel? Where should I put the bucket? And we'll all agree. Again, aside from some weirdness of people being obnoxious and trying to, be nefarious or to debunk something that shouldn't be debunked. So Galileo and this modern student were both amazed by the laws of projectile motion, and indeed, Galileo was so impressed with his discoveries about falling bodies, namely that in successive intervals, the distance traveled went as the odd integers. He knew that the sum of the first n odd integers is n squared. He figured out, this law about 1/2 gt squared, and this emboldened him to make the assertion, the universe cannot be read until we have learnt the language and become familiar with the characters in which it is written. It is written in mathematical language, and the letters are triangles, circles, and other geometrical figures. Very beautiful. And so, this kept going. So, next on the list, if you like, if I'm being a little bit casual about the history of science, is to invoke Newton. This is one of the greatest pages in his great book, the Principia. The figure on the right is one of the great figures in the history of science. I've shown it before. What he's doing is asking the following question. How far does an apple fall in 1 second? How far does the moon fall in 1 second? Both of them are falling towards the Earth. And so you can figure it out. I'm not going to go into the details of it. But the gravity is weaker up there at the moon. How much weaker? 1/r squared, the distance between the center of the Earth and the moon. Newton knew that the distance to the Earth, to the moon was 60 Earth radii. Well, that's cool, because that means the gravity is diluted by a factor of 1/60 squared. That's funny, because now if he evaluates the distance fallen in 1 minute, which is 60 seconds, the 60 seconds squared divided by the 60 Earth radii squared, the 60s cancel, and what we find is the same distance. In other words, distance apple falls in 1 second is the same distance as the moon falls in 1 minute. Very, very provocative and beautiful. And, I note for you that this is from book 3, the most important book in some ways of the Principia, where he's laying out the fact that there's a system of the world that mechanics allows him to understand what he's seen out in the world. So, this is purely just as an aside, but science is not a smorgasbord. If the law of gravity acts between every element of mass on the Earth, then that means the piece just below my rear end, right here on the floor, is attracting me in a stronger way than some piece over in Singapore. And so, rightly so, Newton asked the question, well, how could all of that sum up to act as though all of the mass is concentrated at the center of the Earth? But once again, this is a problem I can assign as a homework, and everyone will agree that they can demonstrate that the gravitational potential of a spherically symmetric object behaves as though all the mass is concentrated at the center. That's what Newton proved using what we now call the integral calculus. Kind of, again, just amazing. So we can move forward in time. In the early 1800s, Sadi Carnot, pictured here, who, by the way, I'm going to have a Science is Not a Smorgasbord about the germ theory of disease. It's very irritating to hear people talking about, is it a conspiracy or whatever, but, real people, such as Sadi Carnot, died at age 36 of cholera. Niels Henrik Abel, the great Norwegian mathematician, died, I think, of tuberculosis at age 26 or something. This is real stuff. It's not some belief system. It's not some opinion. It's a fact. There's an object called Ebola, and if you or I get it, we're in big trouble. It's not a belief system. So at any rate, Carnot was interested in what abstractions could attend our understanding of the various kinds of engines that were being developed. And as I said before, this is something that stood the test of time. So he wrote down a very abstract idea about heat engines, about the efficiency of them. This is something that matters to all of us, whether we like it or not. It matters to us in the context of our electric bill for our refrigerators. It matters for our gasoline bill for our cars. And believe me, the people at Ford Motor Company and all the rest of them are trying to do better on efficiency. But there's certain principles which preside over the subject, which no amount of blah blah will change. So I think it's fun to note that a classic steam engine is shown at the top, a World War II vintage propeller plane engine, or a modern turbofan for a jet airliner. They all have to abide by these laws of Carnot. I think probably of all of these examples, the one from Eratosthenes is one of the main ones that got me interested in science. Is this other one? So this is technical. I don't need to go into the details, but the bottom line is that Maxwell worked out that the electric field should obey an equation which is called a wave equation, just like I would write for waves in the ocean, like I would write for waves in a string, or I would write for acoustic waves. Okay, there's some differences that I don't want to go into, but the wave equations are shown at the bottom here, where you see this upside down triangle. Ironically, Galileo talked about a language whose characters are triangles. He had no idea that on the horizon would come something we now call the gradient operator or nabla or whatever, but it's an upside down triangle. Kind of ironic. And the thing that amazed Maxwell is that he knew that there was a speed associated with these waves. And so the speed depended upon two constants of nature, mu naught and epsilon naught that you see here. Epsilon naught comes up in the static force between two charges. And then this mu naught has to do with if I have a loop of current, what magnetic field will I calculate? So it doesn't seem a priori like those two things together, which come from experiments way over there, that they should somehow penetrate the subject of what light is like. But here Maxwell says, oh my gosh, I calculate that quantity, and look, it's more or less comparable to the speed of light. It is manifest that the velocity of light and the ratio of the units are quantities of the same order of magnitude. Neither of them can be said to be determined as yet with such a degree of accuracy as to enable us to assert that the one is greater or less than the other. It is to be hoped that by further experiment, the relation between the magnitudes of the two quantities may be more accurately determined. What two quantities? A, the speed of light. B, square root of mu naught epsilon naught. And then he says, in the meantime, our theory, which asserts that these two quantities are equal and assigns a physical reason for this equality, is certainly not contradicted by the comparison of these results, such as they are. So, it doesn't matter whether person X abides by or believes in or understands Maxwell's equations or not. Why am I showing you these pictures? Because I think one of the things that has struck me the most in my travels around the world, especially to places that are remote, such as this picture, series of pictures that we took in the Indian Ocean in 2019, just before the pandemic. The thing that you should note is that bottom picture, the two bottom pictures, there's this funny Maldivian boat that surfers use to get around. And the thing I would say is that the crews of these boats, you maybe have 10 people on the crew, 6 or 10. They're all wearing shorts, no shoes. I don't wear shoes for 2 weeks at all. Don't put them on once. Generally don't wear a shirt. What does that have to do with anything? These people are out in the middle of nowhere, literally out in the middle of nowhere, and yet every single one of them every one of them, no exceptions, has a cell phone, and half the day they're sitting and texting. They're often sitting in those boats waiting for us, while we're out in the water, and the whole time they're sitting on their phones, texting with their friends. And, a lot of these islands, what I find is remarkable, you'll see towers on them. The towers have to do with electromagnetic waves and electromagnetic radiation. And again, it's kind of independent of whether this is 1865 or 1905, to signature years in the study of electricity and magnetism, or the 1890s when Hertz discovered that Maxwell's equations worked, or it's now, and we're using our GPSs and our cell phones all the time. My first experience with the GPS was in the mid-1990s in France. And a friend of mine was the head of this park, which is called the High Plateau of the Vercors, Vercors. I recommend you take a look at the map. It's a really beautiful place. It's kind of in the Prealps. It's a little bit to the west of places like like the great parks such as the Parc National des Écrins or the Vanoise, a little bit south and also west of Mont Blanc. And it's this very, very large plain. And we had walked one day, I've been there both in summer and winter, wandered around quite a bit. We had walked to the mountain that you see covered in snow on the right-hand picture, but we were there in the summer. And we, before we left our car, we left it very far away. So it was a long, long day. And we had a very old school GPS device. And my friend Pierre and I programmed the position of the car. And then what we decided is that we would follow the path to the summit. We would just go climb the summit. But on the way back, we would basically follow the GPS. And we would stop when it told us we were there. And so we had a 6-hour hike, and we came back to the car, and it told us to stop a meter away from the car in the middle of nowhere, in the middle of the French Alps, just out on this huge giant plateau, lots of mountains, lots of features. And all we did was to follow what the GPS told us to do. And, again, this is the reason I say it is because people wander around with their phones, and yet then they permit themselves to make these sort of sciences as smorgasbord statements where they say, yeah, I use my GPS. I'll tell you why, because it's convenient. And then some other point, which is maybe not convenient, like whether or not viruses are particles that have a certain size, like 100 nanometers, and whether or not a filter will eliminate them or not eliminate them, or whatever. They're ready to opine happily. So let me give you another example, more biological example of bankable, actionable, indirect knowledge that came from like 1912 or 1915 or something like this. So, the organism Drosophila, the fruit fly, has been a great tool for us to understand things about genetics. And the work of Thomas Hunt Morgan and his collection of amazing students included Alfred Sturtevant, shown here. While he was an undergrad at Columbia, he undertook a very interesting project. And the project had to do with the inheritance of weird characteristics. So what you see is that there's various characteristics that you can observe in these flies. And what they would do is they'd do crosses, and they would ask the question of whether two traits went along for the ride in the offspring or not. The logic they had was that the closer together those two traits were, the more likely they were to be carried together upon genetic recombination. So check out what Sturtevant says. I suddenly realized that the variations in the strength of linkage already attributed by Morgan to difference in the spatial separation of the gene offered the possibility of determining the sequence in the linear dimensions of a chromosome. I went home and spent most of the night, to the neglect of my undergraduate homework, I love that part, in producing the first chromosome map. So what's the point here? The point is that basically by measured frequencies, which I show you here, Sturtevant has these measured frequencies of pairs of traits going along for the ride together. He uses those measured traits in order to make a map long before we even knew that DNA is a genetic material, long before. This is 1910 or whatever, and Oswald Avery and Hershey and Chase happened 30s, 40s, so we're talking decades before. And yet, he was able to define the relative positions of these genes on the chromosome, and they've stood the test of time. Now we have what I would call a science of engineering genomes, where we can make different genes light up. We know where genes are on the chromosome of Drosophila. We can reprogram them so that those particular genes will light up. And again, this is something that any lab in any country at any time can do. It doesn't matter whether you're in China or the United States or France. It doesn't matter if you're young or if you're old, and I will let you fill in the list of other things. It doesn't matter. You will come up with the same conclusion about where the gene of interest is and where in the fly body you will see the fluorescence and so on. So I have a couple more examples. Maybe this one has to do with our understanding of the fossil record and the nature of evolution, which is such an important science, is not a smorgasbord topic. So I love in Darwin, in his book on the origin of species, that he tried to poke holes in his own work. That's the way that we're supposed to conduct ourselves in science. We're supposed to try to make sure we're not fooling ourselves. And so here's what he had to say in chapter 9, which is on the imperfection of the geological record. I look at the natural geological record as history of the world imperfectly kept and written in a changing dialect. Of this history we possess the last volume alone, relating only to 2 or 3 countries. Of this volume only here and there a short chapter has been preserved, and of each page only here and there a few lines. Each word of the slowly changing language in which the history is supposed to be written, being more or less different in the interrupted succession of chapters, may represent the apparently abruptly changed forms of life entombed in our consecutive but widely separated formations. And what I want to say is, in the meantime, the field of paleontology has put together this rich and exquisite record of life on Earth. And I think, there's no examples that I find more amusing and that really raise this specter of the notion of science as a smorgasbord, as do fossil whales. So, in 1983, they were building a nuclear power plant. This is in Georgia. I'm not going to read this to you, but you can just stop the video and check it out for yourself. And what they found is several very, very well-preserved fossil whales, now known as GEORGIACETUS. And I think it's ironic and interesting that, what are they doing here? They're digging earth in order to make a nuclear power plant. What's the nuclear power plant used for? To generate electricity for human beings to heat their houses, turn on their lights, and all the rest of that stuff. The very same nuclear physics that's used to generate the electricity to warm the homes of these people that at the same time want to say, I don't buy the idea of using radioactivity in order to date the earth, and that's the sense in which I'm saying it's not a smorgasbord, in the sense that, the nuclear physics we use to write down a formula for the age of a rock based on potassium and argon-40 isotopes is the same fundamental physics that's used to generate the electricity. And so, I think it's amusing that, even to this day, this is from May 2016, I live near Los Angeles, and we have landfills, lots of them, and they employ paleontologists, and, they found some fossil whales. And, that's not surprising for being in the LA area, because, we have La Brea tar pits, and, we have a really interesting fossil record, say, from the last 100,000 years. So at this point, the fossil record for whales is really very well developed. And again, I want to make this point about self-consistency. Science is not a smorgasbord. We are on one continent, and we want to make sure that when we measure distances between places on that continent, that we end up making the same conclusions no matter how we do it. So, for me, this is really a reflection of kind of a dedication to knowing things. And I love this page from Perrin's book called Atoms, because it shows 15 different ways of measuring Avogadro's number. And there's a few things to take away from this. It gives you a sense in the year 1910 or so what the error bars are on how well one can measure Avogadro's number. So this gives us a sense of scientific uncertainty. It also gives us a sense of the consistency of incredibly different things. The blueness of the sky, black body spectrum, radioactivity, viscosity of gases are very different things. And yet, when we do our science correctly, we end up coming to the same conclusion about the number of molecules per mole, which is roughly 6 times 10 to the 23rd. So this is the things that I wanted to say by way of introduction to my sort of science as smorgasbord theme.